Well, good morning, all. For the first time in 22 years, I don't say I'm here from National Instruments or NI. I am here today from SpaceX. I spent 22 years in LabVIEW R&D building the language that a lot of us use. And after 22 years, I decided, let's go see if I can use this thing. Turns out all of the controls are in exactly the right place for me as a user. I just have to think, where would the developer have put it? And it's right there. This language works great. I highly recommend it. I work on Falcon and Dragon. For those of you who haven't been following the news, Falcon is the main rocket. The Dragon is the little capsule. Yesterday, we docked with the ISS on the Axiom 2 flight. I work on ground software, which is all of the ground control systems up to about T-minus 30 seconds that control liquid oxygen, rocket propellant load, monitor for all the conditions on the ground, coordinate all the telemetry coming off of the rocket, and manage the recovery boats and all the test pads. So it's quite a sprawling system of applications, and it's written in LabVIEW. I work on it, and I've been there for almost a year now. Today, I'm falling back to talk about LabVIEW, and I'm not actually going to spend much time in LabVIEW itself, because what I'm going to talk about is more of the conceptual side, is why is it that LabVIEW actually is an effective language? It's not as tightly tuned as C. It doesn't allow you to express, do this at the register level. It's not got the high-level controls of a C#, and yet it is highly competitive, and in its proper domain can be light years ahead of these other languages. So there has to be something to it that is buying it, and it's not just that the folks at NI are really spectacular programmers. It's that there's something fundamental, a really core idea that makes it a fundamentally good foundation for software. And that foundation is something called Dataflow. So this is a potato on a pedestal. But it's not quite a potato on a pedestal. It's a picture of a potato on a pedestal. And that's an important distinction that we're going to talk about a little bit today. Now, I can take away the pedestal. When my nephew was 5, his mother had an iPad in the kitchen with a recipe on it. And there was a picture of a potato on the screen, and next to it, in the separate column, was all the text with the instructions for this recipe that she was making for dinner. And my very insightful nephew is on the kitchen stool looking at it and goes, "Why doesn't the potato fall down?" Because it's just floating in space. And as far as Caden knew, things that don't have support under them should fall to the ground. And so we kind of got into this discussion about, things don't just fall with gravity. Well, bright kid points out, well, Mario falls. He walks off the cliff, he falls down. True. So we get into this discussion of, well, if we want something to fall in software, we actually have to teach it how to fall in software. And we have to, describe what it is that we want these things to do. So he's like, is it a magic potato? And no, it's not a magic potato. It's not even really a potato. It's a software representation of a potato. And if we want it to behave more and more like a potato, we have to keep piling on all the pieces that make it a potato. This led me to an idea, trying to explain this to the 5-year-old, and when slowly trying to tell this story to other engineers. We can start thinking of the whole universe. What if we, what are the rules of the universe? We can have a string of zeros and ones, and each one represents some coordinate in space, and maybe it's an enum of which subatomic particle is there, and of course there's a zero case for there is no subatomic particle. And they have quantum superimposed enums, which allow you to represent 2 particles in the same space. But you bear with me here. We can keep adding rules to the system. We could look at the universe itself as a computer, this giant string, and each Planck moment, we go from one state to the next state. A bit moves from here to there, and a result, we render on the large 3D space that is reality, the new state of the universe. These computations are happening continuously. And so if you think about it, if the best way to simulate how does a potato fall would be to actually drop a potato and let the universe compute how does a potato fall. Because at some level, if we turn the usual model around, that's what's happening, is that the potato is going through computations of resolving all the gravity vectors and the air resistance and everything else, and ends up on the ground, at least when you're inside a gravity well. If you're on a rocket, it might go somewhere else. This idea of looking at the universe as a giant computer leads to an interesting question. We use software to model the universe. What if we turn it around and ask, what does the universe teach us about software? And that is the jumping off point for this data flow idea. I need 2 volunteers, or this is going to be a very short presentation. Derrick. I need 1 other. All right, back in the back. Come forward. Now, I am reliably told by the internet that for the last 20 years, the single most popular candy bar in the world, globally, is a Snickers bar. They have mastered the art of putting fat, sugar, and salt together in exactly the right quantities, and it makes everybody happy. If it doesn't, we're going to also have a very short presentation. Matt, Derrick, I need you to share this candy bar. Go ahead.
Share it. Well, you can open it. No.
So notice what's happening. They're having this negotiation, trying to figure out what is the best way to go about it. They're having to figure things out. Okay, they've decided that the right way to do this is to break it in half, and you may go ahead and eat it. So we can think of eating a candy bar as sort of a data transformative process. We have an input, the Snickers. We have 2 processing units. That's what you've been reduced to. You're my CPUs that are consuming and producing. It produces output. We won't be discussing the output today. But these processes are taking this in, and they needed to operate on this same piece of data. There's 1 candy bar that they were both going to consume. We talk about producers and consumers. This is how it happens. You may sit down. You're welcome. All right, so they did this. I need 2 more volunteers. I promise there's candy in it. Right back there is 1 and 2. Come on forward. This is a Snickers bar. I need you to do it. Find a way to share the Snickers bar without breaking it first. What do you got? What are some ideas? Throw them out from the audience. What could they do?
Lady in the Tramp.
Lady in the Tramp, right? What's another option besides that?
Melt it.
One gets the wrapper.
What was that back there?
One gets the wrapper.
One gets the wrapper. Okay. The easiest one, as we said, is both biting on it. What if they were to timeshare it? What if one of you took a bite and then handed it to the other, and you could eat from both ends? Well, it won't make you eat all the way down to the middle, but for COVID reasons. But you could share it back and forth.
Yeah, but I have to open it first.
True. So one of you needs to open it first, and then you could share it. All right, you 2 may go ahead and break it and take it on back to the thing. You've served as a useful object lesson. So, would that be romantic, or is it just sore noses? I've always wondered about that scene. It's a little weird. But it's a useful metaphor. It's even got the spaghetti programming right in there. There's actually multiple options that we could come up with. So we have the breaking it in half. We've got time sharing. You take a bite, I'll take a bite. We just keep handing it back and forth, and we'll eventually consume the whole candy bar. We could do simultaneous access where we're both chewing on the same end. That's really complicated. And then the one that's really not biologically feasible, morphological integration, where we'll just put one head and have multiple stomachs coming off of it. Believe it or not, that's a photograph. They just happen to be posed exactly the right way. Took me forever to find a way to line that up. A single consumer that is taking it into two back-end processes, but that are somehow tied together in the same loop. All of these ways of consuming the data as it comes in are things that we have to do and manage, and we come up with different ways of doing it. And if you look at your LabVIEW code, you get your producer, your consumer loops, you get your forking out to different processes, you get distributed computing when we get up to the macro scale things. All these techniques for sharing this piece of data. But what's weird about it, when you stop and think about it, we're not exactly sharing the same piece of data. It was one candy bar. But did they eat the same block of chocolate? No, they broke it in half and each of them consumed a chunk of it. Keep that idea in mind. We're gonna come back to that. At some level, we're always either breaking down the data or copying it. There doesn't seem to be a way around that. There's like a fundamental aspect of the universe that a thing doesn't like to be in two places at once. And that is as fundamental about physical matter as it is about information. You start getting into caching levels and all of this, and it's all about trying to share things around. All right, I need another pair of volunteers. This one's easier. One. And a second one.
Come on, guys.
Come on up. There we go. Back there. All right. I promise this one's easier. This does not involve noses. We've just talked about writing the data. Now we'd like to read the data. So we have the back of the thing. I'd like you to somehow, both of you, read aloud that the back of that Snickers bar.
Hashtag eat the Snickers.
Packed with nuts.
Milk, chocolate, sugar, cocoa butter, chocolate, skim milk.
Milk, lactose, milk fat, soy, nuts, corn syrup, sugar.
A lot of healthy stuff.
Mm-hmm.
Yeah.
All right. So they're reading back and forth. They've decided to hand it back and forth. But notice they're keeping their heads together because they're both trying to get access to the same piece of data. And you notice how it's not natural. They're kind of having to fight their way in to get enough space. And everyone's, doesn't have quite enough breathing room for normal interaction. That's what happens when you try to get processes all trying to glom up on the same data. I will give you both a separate candy bar and you may head back to your seats. Thank you. So their heads tightly close together so they can both see. That's one way we can read together. We can have one person simply read it aloud and the other person hears it. And it's a sort of way of okay, it's being read, but it's being shared with everyone. It's almost as if you're rewriting it into a new form that's easier to distribute because you translated it from this physical picture that only one person could look at to the sound which broadcasts. We can wait for one to finish. One person could just read it and then hand it to the other. And we end up with serialization, time. And we could project it up on the screen. We could make it so that it's easier to access. And we could put it up there and make it big, and then both of them could stare at it. If they turned around and looked, we had it back there, in fact, which would have made things a lot simpler for our volunteers. Again, just like in the writing case, the consuming case, we have some issues that keep cropping up. When they were trying to hand it back and forth, they're trying to shift it back and forth. If you're trying to read at the same time, you get these problems of who throws the wrapper away. What if the other person is still reading it? You end up with these timing problems of everybody trying to share the same copy. And it's far simpler for them to just both read it when I hand them both a Snickers bar. Everyone gets their own copy, everybody can read. So data sharing is a thing we want to be able to do. Because, wait, why? Why? Oh, because copying a Snickers bar is expensive. Buying extra secrets bars is hard. We'd like to only stick with one, but it's easier when we can clone them off. And there's this tension between how many replicas of the data do you need in order to not literally starve your processes versus how many ways can you share it and get your heads closest to the data so that you don't need to replicate it. That physical tension that we see in reality, every time you have a meeting where you're trying to disseminate information, every time you have a document that you're trying to share, whether it's an electronic document or an old physical paper document, this tension of information constantly crops back up. And half of our organization management processes are all about trying to manage how do you disseminate and share the data in a reasonable form. And what's really weird when you really get down to it is that all data sharing is an illusion. Because while we said, oh, they're both sharing the same candy bar and they're both reading it, they're actually not reading it. They're each getting a separate stream of photons to their eyes. The data is being copied by nature because we can't put their brains in the same place. We can't make it so that they're actually receiving the same data stream. They're each eventually getting it from their own perspective. And information has to be disseminated if you're going to have two processors for it. Over and over, you'll find that we are not really trying to share information. What we're really trying to do is control what level of caching that information has to be shared at. And we want to make the copy at the least expensive level. Making duplicates of the photons, dirt cheap. You can both hold your heads together. Everybody can read their own photon stream. All you need to do is turn on a light in the room. Physics takes care of the rest. Making a second candy bar costs a bit of money. You got to shell out, make sure you have a second one on hand. There's a big jump if I was to say, no, we need to replicate this candy bar. Someone's going to have to run to the store versus we can just both read the photons. So it's your caching levels. When we start looking at CPUs, L1, L2, L3 caches. When we start looking at networks, how much buffering are we doing? What are we doing as broadcasts? Are we pipelining the data through a series of owners so that each one can have their fingers on it one at a time? Or are we actually producing data copies so that everyone is able to process it all at the same time? You have to, when you want to really start thinking about the fundamentals of information science and information theory, you slowly will recognize there's no sharing that ever happens. There's only controlled levels of caching. And as we all know, caching is one of the hardest problems in computer science because it is very easy to get them wrong. And replication of information means there's multiple sources of truth, and you have to run into all these problems. So, data flow. All of this thing that we're talking about, this information, is all data flow. The information flows from the candy bar through the photons to two processors. The information flowed from me to the two processors I was handing it to. As we chain these things through, the data flows to different processors. And what data flow is, when in a programming sense, is declaring who are the dependencies, who needs this information. LabVIEW, you don't have to get into specifying this is a memory allocation. This is an explicit copy. This is a place where I need to actually share the pointer, take an address. We get rid of all of that, and instead you run the wires together between the nodes, and all you're saying is these two nodes depend on this same upstream input. You don't declare the rest, because that's enough for the compiler to go, okay, I can figure out the optimal level of sharing. So a model of parallel computing that represents programs as dependency graphs, where each operation waits until its input values are available. There are many data flow models. Typical LabVIEW uses a synchronous data flow model. Data arrives, the node executes, passes it downstream. The next node gets the first input, waits, gets the second input, waits, gets the third input, finally has enough information, executes, passes it downstream. Everything is very synchronous and flows through. You throw in the channel wires, now you have some asynchronous data flow, but it's still data flow. You have a loop running over here, and when it gets a value done, it passes it through the channel wire to the second loop over here. It's happening asynchronously, but there's a clear handoff of the data to the next loop in line. And we get nice laminar flow of data. You can do the same thing with shift registers in a pipeline. People who are doing FPGA programming frequently will have a lot of pipes moving the data through the FPGA fabric. All of these data flow paradigms, they all are fundamentally are a set of nodes connected by wires at different levels of metaphor. And in LabVIEW, they're physically graphical on the screen, and in an FPGA, they're physically, on the fabric. That is moving data through, and we declare it, and we say, compiler, you figure out where to make the copies. We provide the guide to the machine. We don't give all the fine-grained details like you would in a C program or writing a fine-grained assembly code. Instead, you give a high-level definition of here's who needs it. How soon? Is it an asynchronous link? Is it a queue that is going to have buffering? Is it a network connection that is going to have latency across it? How much sharing is possible? I can branch this same input to these 3 locations. Okay, so that's how much fan out is possible. We declare this and let the compiler solve for the optimal way of doing the sharing. Now I say optimal. That of course depends on, first of all, that NI has got all of the bugs worked out, and also we keep finding new ways to do the optimizations. But that's at the heart of it is the more the optimizations are found on the back end, the more valuable that data flow graph becomes. And if you start looking at textbooks for C++ and C# and all these other programming languages, how do their compilers make big strides forward in performance? It's all about recovering the data flow from the text that's given. You declare a bunch of variables, you have some calculations, you have some things that use those variables, and they have to analyze the code and figure out the dependencies in order to, okay, this can go in a register, this has to spill out of the register, this can sit in the cache for a little bit longer because it's valuable, we'll pin it. All of this recovery of the data flow is something LabVIEW doesn't have to do because you, the people with the business logic, spelled it out explicitly. Data starts here and it needs to go to these 6 places. And that, at a root cause, is what lets LabVIEW stay competitive because we can branch out to all of these parallel processes and keep them staffed with data and minimize the overhead of doing all of that work. So I said there wasn't going to be much LabVIEW code, but there is a little bit. So we have 2 readers. So we have an array coming in, and they're both going to search the array. Now, a lot of people programming LabVIEW, especially if they come from another programming paradigm, become very panicky about that forked wire. Because they're like, oh, well, now I've made 2 arrays. Conceptually, you did. If we want to, if we are looking at a program correctness of a LabVIEW block diagram, anytime there's a wire fork, those are completely independent forks. There is, the data goes off to one place, it goes off to the other place, and we never worry that something that's happening down here is somehow going to change the value that's up there. We just don't worry about it. LabVIEW, the compiler, worries a lot about it. And what it's doing is it's looking and going, hey, those are both read nodes. They're both reading the same array. Behind the scenes, that means I can just take the same memory address and give it to both nodes and let them both chew on the same data. No reason to make a copy. Contrast that with this model where I have 1 reader and 1 writer. And you're like, oh, well, now if I were actually to take an array in and this guy says, oh, I don't need to make a copy of this. I can just modify the existing array and delete an element from it. Well, we can schedule that. Well, now we have to have a copy because the read-only went up top. And so we duplicate it and do it. But then the compiler gets a little bit smarter and says, nah, we don't need to make a data copy. We just need to schedule those nodes to happen in order. As long as we search the array first, and then we delete from it, we don't need to make a copy. And then a few years later, the compiler gets even smarter and it says, actually, delete from array doesn't need to modify the array at all. It could just take it in, and what it could output on the other side is a subarray that's just a pointer back to the middle of the original array. And we can just use that new address going downstream. If you ever look in the context help window and you see subarray coming out of some of your nodes, it means the LabVIEW compiler has optimized that section to say, I don't need to duplicate it. I can just borrow a pointer into the middle. Each of these things is somehow slowly figuring out, based on the data dependencies and the requirements of each node, all of these optimization levels. Now, of course, if I finally do hit 2 true writers, and they're going to actually modify the array and do something in here, then yes, we may actually have to make a duplicate. Turns out the compiler has gotten a little bit smarter these days, and it can do a subarray on both of those halves. But it's doing the analysis, it's figuring out the requirements of the nodes, and it's having to solve this question of, do I need a copy or not? None of you, and now none of me, have to worry about that. That's all a problem for the LabVIEW R&D team now. And that's the advantage. That's where we're getting these incredible performance boosts from LabVIEW, is all of this reduction of caching. And the reason we get development boosts is because we are not having to spend our time thinking about all of this. The compiler is chewing on all of it and figuring it out. And as long as it's doing all of that work, that relieves us to just worry about the business logic of which index is it that I really need to delete. The more that we allow the programmer to focus on the business logic and less on what does the computer need to do, the better. We can end up with some more complex situations where we actually have 2 loops, both modifying the array in different directions. Here, we absolutely have to do some amount of copying because we're either producing brand new arrays and actually, where we're sharing the pointer up front and producing 2 different arrays, or we're serializing them so that one makes a copy and then the other one can modify in place. Do I know which one it is? No. The LabVIEW compiler a long time ago got smarter than me. I have to actually open it up in order to pull these things apart to figure out exactly which case is coming from. I happen to know for this particular simple diagram because I've looked at it, but in general, I don't worry about it. Sometimes, how many of you program LabVIEW RT, real time? A few of you. Sometimes we do have to play hide the dots, where we have the show buffer allocations. And the buffer allocations are places where we annotate the block diagram and we go, yep, these are the points where LabVIEW felt the need to allocate a buffer. That's not necessarily the same as making a copy, because some of those buffers are just there in case of various situations. And it may be that it created a buffer allocation for a subarray, not for the whole array. But in general, buffer allocations are places where it said, I can't keep sharing, I'm gonna need a new value here. And so we go and we say, look, today, in this very rare case, I happen to be smarter than the compiler, and I can go in and add some custom nodes or move my order of my nodes around with flat sequence structures and stuff to force a particular timing and give the LabVIEW compiler a little bit more information than it usually has. But those are getting rarer and rarer as the compiler gets better and better. And as time goes by, that analysis hands off more and more work from us and lets us focus on, is this the right code for, in my case, flying a rocket? In your case, running a test system or building a car. This morphological integration that I was talking about before, this is how you would do it. You take your 2 independent loops and you fuse them together into a single loop. Now, we have very clear indication we only need 1 copy of the array and we can do something with the fields. And we get a different compilation between these two. Because in one case, LabVIEW says, I'm gonna give the bias towards being parallel. And I'm gonna let these 2 loops happen independently and let the threads go for it and compute through as fast as possible. And one may finish before the other. Whereas in this case, it stays locked together and it's gonna finish at the same time. And so as a result, it decides to do a different copying pattern for the information. Ultimately, what we can see is that Dataflow works because of 3 factors. The first one is it prevents you from bumping noses. It keeps you from having to worry about who is accessing a given piece of data and trying to get all of your processes chewing on it at the same time. It avoids pulling the candy out of someone else's mouth while they're still eating it. Because that wire fork, it's thinking about it and going, oh, you need it first, I'll schedule this one to go second. Or I'm gonna make a copy so that they're completely independent. And It prevents you from buying more candy than you need because it only makes a copy when we actually need a copy. And if it can just do it based on photons reading the same thing, it'll use the photons. The LabVIEW compiler under the hood can do a complete memory copy of the array. Or it can create just a subarray with a pointer back to the original. Or it could just load some values into registers and move them through. Or it could copy just a single sub-element out. There's lots of aspects of ways that it can do the sharing, and it's going to do the evaluation of all of these as it's working its way through the code. We as programmers, though, have this never-ending quest to fight the data flow and to share data somehow. And we keep coming up with new technologies, and because I've been gone for a year, I'm sure that this list is short. There's probably a LabVIEW 2023 demo of a brand new way to share data because it's an ongoing frustrating problem. All these different technologies come up as ways of creating multiple processes that are sharing information back and forth. Some of these are ones that I recommend. Some of these are not. And the difference between the ones I recommend and the ones that aren't are which are the ones that most play well with the data flow? Which are the ones that fight against the data flow? The more you fight against it, the more problems you create and the more debugging headaches or timing problems that you're going to have. So I have this term called data flow safe, which is a vague term. It doesn't have a precise scientific definition. It's a guideline, not a rule. But essentially, all data is usable by one and only one process at a time with a clear handoff to the next process. So sometimes that's just math nodes in a row. First it does an increment, then it does another increment, then it does a multiply by 2. Each node has its hands on the data one by one. Sometimes it's a producer-consumer loop. The producer has its hands on the data, it puts it into a channel wire, the consumer loop at the bottom dequeues from the channel wire and chews on the data at the bottom. Sometimes it's a more complex broadcast through an event structure or a network graph. But when data is data flow safe, it means you have rules for this data should go over there, and I'm done with it. I've given it away. I no longer have it in my hands. Contrast that with a data value reference, a DVR. There are some safe use cases for DVRs, but the most common use of DVRs is you get one process that is going to do the unlock, modify the value, lock it again. And the other process does an unlock, modify the value, lock it again. And they constantly are tensioning back and forth between each other because one of them can't go while the other is working on the data because they're trying to share that information at the same time. So if you can so data flow safe is a goal of trying to get to this point where I'm no longer trying to actually simultaneously share data. I'm defining my world in ways where I'm handing off the data in well-defined timings. So what do we got some examples? Well, if we can use all by value types, that's data flow safe. I can run a simple numeric through and do some math calculations. I can run a string through and do parsing of it and piecing it out and breaking it into an array that I then send downstream. I can run a channel wire. Channel wires have a well-defined input and a well-defined output. They, when they have fan out, they define these are the read points. This is the write point. You don't ever get them confused. You don't try to, and you've given the compiler enough information to understand what it is you're trying to do. Directed queues. If you create a new queue, called the obtain queue, and you fork it out to your producer and consumer, or to your producer and broadcasts. There's a well-defined, this is the enqueuer, this is the dequeuer. When you try to create these feedback loops where people are working back and forth on the same queue, or you cheat and you use the single element queue where you read out and then you block, some of you are nodding and you've played this game, that's abusing the queues because now you're creating tension where both sides are having to wait on each other. Action engines. Those would be your LabVIEW 2 style globals, a term which is getting increasingly out of date. LabVIEW 2.0 being very far back there. But basically an uninitialized shift register in a non-reentrant VI that remembers its value time after time. you can call in and it does its thing internally. And we're going to come back to that one because there's a caveat on it. User events and notifiers, those have a nice well-defined flow. This is the writer, this is the reader. And unforked references. If you can say, I can write the data here and then I can send it and it clearly goes over there. There are several use cases where unforked references, that one's got an asterisk by it because not all of them are safe. But it's one of those where you can look at it and go, I might be able to get some good data flow here. The unsafe ones are all the things we tell you never to program with. The global VI, which is uncontrolled. It's dead easy to use. There are some edge case use cases for global VIs. I have one particular that I like, but in general, they're a bad problem because you don't have any controls on the data. Everyone's trying to share it. You end up with stateful problems, and we tell you don't do it because LabVIEW can't optimize a darn thing about a global VI because it doesn't know how the data is supposed to move from it. So every read from a global VI has to be a copy because somebody else might need that value. The one element queue trick that I was just talking about, if you don't know about it, I'm not going to teach you. Functional globals, where all you have is you have the uninitialized shift register and you have read and write are your two operations. Really, all you've done at that point is you've just created a global VI with more overhead. If you can keep your operations inside, like an action engine, that's good. That's all the data flow. You've handed off information. It's processed inside the sub-VI. It's a nice bottle. If you're trying to do read and write operations on this shared piece of data, we're right back to data sharing between two processes. Not good. And you might as well use a global VI. Forked references, shared variables. Shared variables are just bad. You think global variables are a problem. Shared variables are universal problems. They're things that everybody can access far beyond your local code. I like them particularly for getting information from the FPGA back to your host. That is a great use case for shared variables. They are really well tuned in that. Most people don't try to use them in a controlled manner. They try to use them as some sort of massive sharing databases. There's much better processes for massively shared databases. And the last one is forked references. Now, obviously, if you obtain Q and you fork the reference to a producer and a consumer, that's a forked reference. So they're not all bad. But anytime you have a reference that you're forking to multiple places, you have to look at it and go, is this really a good one? Is this actually acceptable? Can I trace the flow of data and show it's going from one place, it's handing off to another? Any questions about this list?
What was your use case for the global VIs?
The use case for global VIs is if I have a config file where I read it at the very beginning of my program, and I need to read, so I write it one place, and I can read it in several independent places downstream. But I need to be able to read it once in all of those other things because every read from it is a full copy. But if I can use it just during initialization and I can do that, it can often simplify down. I usually will scope them inside of a class, make the global VI private, so I'm very clear who are the accessors, and I can limit it down. So that is an interesting case there. There's a couple of others that have cropped up as edges, but that's the one where you'll usually see me reach for one, because it's a nice, easy way to just say, that's my configuration. Also, they're easy to debug because at any point I can pop open the front panel and go, hey, look, there's my configuration.
It's a related question.
Yeah.
Is it possible to have the global VI be a read-only to prevent those copies?
It is not. We would need some sort of statefulness on that to make that happen. And that is not something that has ever been implemented as an option. Probably because we try to advocate against using them in the first place. And so keeping them a little bit more protected is better.
Since I was asking questions, we get a microphone if that'll help.
And I should be careful to try and repeat the question if I can, so sorry. All right, so how do we work within the data flow? What's a better way? Oh.
Yeah, I have one question. Where would local variables within a single VI fall?
They're a mixed bag, but in general, they create cycles of information where you're writing to the terminal, you're doing reads and writes. So most of the use cases for local variables are problematic. There's some very good ones, particularly for UI programming, where they're good because they're kind of like directed cues back to the screen. So they're on that. I look at them askance and I have to go, is that actually a good case? All right, so to stay within Dataflow, first off is run wires wherever you can. Don't try to hide data off in a global variable or a DVR or a shared thing or any other thing. Just wire it. By wiring it, you actually make your testing a lot easier. Because if you're testing your system, you have to make sure that all of your global pieces are initialized properly before you can call your sub-VI. Whereas if your sub-VI takes all of its inputs, executes, and produces its outputs, you can run test code on that, really simply. You put a different test case in, wire it up, see if you get the right output. Put a different test case in, wire it up, get it out. Code that runs with bi-value wires is, and that takes all of its inputs in, doesn't try to share with any other location, is easiest to test, is easiest to understand because the whole focus is right here. It's reusable. You can pull it out and take it to another system without having to take all of the pieces along with it. There are so many advantages to trying to just stay within the wires. And I see a lot of people fight against it. And I've got this super high VI up here and there's 3 levels of sub-VIs and I need the value down here. I'm just gonna stick it to global. No, take the time, connect it through on the connector pane, wire it through. If you go onto ni.com/LV menus, you'll find a little tool I wrote called the wire drill. You right click, it's a right click plugin. You right click on one terminal and you say start drill. Right click on another terminal, you say end drill, and it'll connect it all the way through or go up the other direction. Even works through dynamic dispatch VIs. Take some of these times to do the actual routing of information. You'll be a lot happier in the long run. Execute VIs, pass data. Don't try to get this backwards. When we try to create these things where a DVR is a thing, then we're gonna check it out, do some operations on it, and check it back in. That's kind of treating the data as a living object, as the thing that is doing this execution and has all this state. Whereas what we really would like to get to is a mode where we run a VI that operates on inputs, produces outputs, passes it down synchronously or asynchronously to the next executing VI in line. DQMH, actor framework are both based on this predicate of we spin up a bunch of actors or of loops that are handling all this and they pass messages between them. The more you can write your code to think about it in terms of I need a process and that's the thing that's going to run rather than I need a shared piece of data that we're all talking to. If you try to, a lot of C++ textbooks and C# textbooks will teach you to think in terms of one object talking to another object. And this does something to this other one and they're parts of speech. That mindset creates tension and threads that have to work with each other. Whereas if you think of it as processes handing off data, you'll get a whole different architecture picture in your head, I promise you. I've taught that to many developers over the years as I've gone into different customers and tried to show them things. And the pictures you will draw on paper just when you're planning out your software are very different pictures. This is sort of the transition here in the actor framework. We start with an actor, it starts as a bi-value object, we initialize it. It's flowing as a value down that thing. It's not a living being yet, it's just data. Then we launch the root actor, and now there's a new VI running, and that VI is now a running process, and we send messages to it. We didn't stick it in a DVR that you're constantly checking in and out. And what you get out is the enqueuer that you can enqueue messages to it. So we transition from synchronous data flow to asynchronous data flow. This is a trickier one. This one is a little bit more higher level. So I start off with the one that I know everybody can get, run wires. And we're gonna work our way up. Announce instead of request. A lot of software gets written where I'm gonna make a request. I'm gonna send a message to that web server and say, give me this web page back. It's a good model. It works for the entire World Wide Web. So I'm not gonna say that it's a terrible thing. But when I send you a request, what am I doing while I'm waiting for you to get that request back? Well, I'm waiting for your response. I'm sitting there waiting. And if somebody tries to talk to me, I'm ignoring them because I'm waiting on this response. The other way to do it is to phrase it as, I need this data. and then I'm going to go about my business. So if you try to talk to me while I have announced that I need the data, we can have a conversation. And eventually someone over here goes, hey, I have this data. And they announce it. Oh, I hold on this conversation. I need to go handle this. You get into a much more asynchronous mode where your processes are constantly live. They're able to respond to things because data is being passed as a message, not as a locking event. That's a very different mindset, but it's consistent with Dataflow, is that instead of trying to tie two processes together and have them share a state, it's a little bit more complicated than sharing data, but sharing a state where we're now in the mode where I'm getting information. I'm now in a mode where I'm simply needing data, and I've let you know I need the data, and I can go do other things until you eventually get me the data. And again, if you're ever working Actor Framework or DQMH, they're based on this principle that we want to share this data out. We want to free up our processes to be able to work as much as possible. Now, before I get to the fourth one, I need 5 volunteers. 5 volunteers. 1, 2, grab a chair. 3 more. 3, 4. There's Candy. 5. All right. Everybody grab a chair. Now, what you're going to do, A, B, C, D, E. Gotcha? Everybody remember your letters? All right. I am going to be the producer. I'm producing widgets. You are my test line. You're my inspectors. And what you're going to do is you're going to look at each of the stickers, and on the back, there's a letter. If it matches your letter, set it down in your chair. You're going to be standing up. If it doesn't match your letter, pass it down the line. At the end, if it doesn't match your letter, you put it on the table. Just create a pile of the pieces over there. Everybody else, we've accepted it along the way. As soon as you get the last Snickers bar, sit down. All right? So stand up. And we're going to go producing this. So just as quickly as you can, glance at the letter, either set it in your chair if it matches your letter or pass it down. Go. All right, now I want everybody here watching. See what they're doing. See? There's eventually the pipeline is filling up and we're getting all the way down and Snickers bars being produced and there you go. And as soon as you get the last Snickers bars, be sure to sit down. Now, all right, so let me open this second bag here. You didn't get the last Snickers bar. Why did you sit down?
Made a mistake.
Ah, you checked for an empty queue before and decided that that was a good reason to stop. All right, how many of you have done this? Where you start checking, oh, the queue is empty, therefore we must be done producing widgets, and so we exit the process. This is a very common mistake. But there's always more data. What you really needed was a final Snickers bar that somehow indicates I'm the last Snickers bar in line. And I tell you, the last Snickers bar doesn't have a letter. And now you know, oh, we're done. All right, you guys can go. Take your Snickers bars with you. Ah, one down. All right, so the fourth one is to make sure that you embed your stop signal in your communication channel. And this one seems a little weird, like it's not quite data flow, but what it is it's about keeping your data flowing together. Instead of creating channels that are going both from the same source to the same destination, flowing as independent pieces, you try to tie them together to some sort of internal connection. And as long as we signal that within the data itself, that there's more to come, there's more to come, there's more to come, and there's a separate bit that says, this is the last piece, you end up with data flow that knows when it's done. You solve the problem of when do we throw away the wrapper? When are we, when can one person stop reading and let the other one free the resource? It's part of this data flow aspect of keeping all of the data flowing together when it's meant to be a package deal. It's the same concept as when we create clusters and we say, This is a block of data. When we create a class, this is not just a block of data, this is a block of data with an identity and a behavior. Trying to tie these things together as you build your bigger and bigger systems and more asynchronous, you'll begin to eliminate one of the most common bugs that I see in a lot of G code, which is the inability to stop or to hang when you hit exit, and sometimes not every process shuts down, or you deadlock because somebody quit early and everybody else is waiting on it, even though it's no longer accepting data. This last one is a critical piece. How many here have ever heard of the codeless code? Oh, good. This is my chance to introduce you to it. This is one of my favorite websites. It is 256 one-page short stories about a group of monks that have to program a web page. And the lessons that they slowly learn over the course of developing the code. And case number 48 is the problem of the 4 silences. And I encourage you to review it. I assure you, you will learn a lot reading the codeless code. And they're very brief. You can share them out with your team. I reference them a lot on my team. And sometimes when we have one of these deadlock situations, I'm like, you missed the silence. There's the silence between packets, and it's very different from the silence after the last packet, even though they sound the same. All right. My team is hiring. This is my presentation, and if you would like to join in, we have open recs. Everybody from NI, close your eyes. I'm not allowed to hire you right now. But for the rest of you, SpaceX.com/jobs, these are the 2 that are open on my team. We're looking for skilled G programmers. If you're interested in writing LabVIEW code that makes rockets fly, we're not actually on the rocket. We're like I said, the ground control and the recovery boats. We're looking for both entry level and senior developers. So if it catches your interest, I always like to point out this is a photograph, not a rendering. This is the Tesla in space. We do an awful lot of amazing work. Yesterday, we put 4 astronauts onto the International Space Station in record time with a 15-hour from launch to the station, setting new records there. We do a lot of interesting projects, and SpaceX is continuing to develop in all sorts of other fronts. So if you're a skilled programmer and you like that sort of thing, please give us a chance. So, if you get nothing else, if all of this was just completely confusing, wires are good. I want to make sure you walk out of here with that. Are there any questions? To the back.
How do you deal with LabVIEW superstitions? For those of us who don't have access to the source code of the compiler, we all develop weird superstitions of when I should use an in-place element structure and when you should absolutely avoid it without much proof. How do you anchor your LabVIEW superstitions?
How do I deal with it? Well, I get myself hired at the company so that I can then start correcting them. No, when I got to SpaceX, there were a number of those that have developed in the code. It's a little hard to explain. Well, the first thing is you go to courses in iWeek, places where the latest and greatest things are being talked about and are being discussed. You participate in the forums to share things out, and the same as you do with any other internet rumor, you post it and you go, is this really true? Most of them have been debunked at some point out there. Like every wire fork is a data copy, so you should never fork a wire. No, that's just not true. And for the most part, you let the compiler worry about it is the right answer these days. That's one of my favorite superstitions. Or LabVIEW has a garbage collector and so it's really slow. No, LabVIEW doesn't have a garbage collector like C#. It's just, that's how things work. You can find presentations out there from various people, LabVIEW R&D, all the way over into CustEd, doing customer education courses. We try to directly address those in the courses that we wrote there. And the new content that NI continues to develop tries to address that. That's really the biggest one, is just when you hear one that sounds odd, check it. And check it when you upgrade new versions, because a lot of them go stale. They used to be true, they're not anymore. Any other questions?
Yeah, do you use any framework in particular at SpaceX?
I am not allowed to talk about our internal code. There are ITAR restrictions and things like that, so I can't get into the details. I can tell you that if I was developing prior to SpaceX, I would highly recommend the panel manager for UI development. It's my favorite way of building user interfaces. Derrick, while he was at MGI, built the panel manager. And that's a particular framework that I'm very fond of. There's a number of other tools out there, but yeah, I can't talk about what's inside SpaceX. But if you send me a resume, you might be able to find out. Anyone else? All right, I have sticker bars up here at the front. I do not wish to take them all home, so if you're wanting them, please come up and get them. Thank you for coming.
Thank you, everybody.